Today's lesson is about integrals of trigonometric functions. At the end of this lesson, you must be able to solve problems involving integration of trigonometric functions and to apply trigonometric identities to simplify the function or the integral. Here are the basic formulas for integration involving trigonometric functions. We have the integral of sine u du is equal to negative cosine u plus c. The integral of cosine u du is sine u plus c. For the integral of secant squared u du, it is equal to tangent of u plus c. And for the integral of cosecant squared u du, this is equal to negative cotangent of u plus c. For the integral involving the product of secant u tangent u du, this would result to a secant u plus c. And for the integral of cosecant u cotangent u du, this will lead us to negative cosecant of u plus c. These are the basic integration rules that would involve the trigonometric functions and would result to a trigonometric function as well. We have supplementary formula or rules as follows. We have the integral of secant u du is equal to ln of the magnitude of the sum secant u plus tangent u plus c. For the integral of cosecant u du, it is equal to the natural log of the magnitude of the difference between cosecant u and cotangent u plus the arbitrary constant c. Having the integral of cotangent u du would result to the natural log of the magnitude of sine u plus c. And for the integral of tangent u du, it is equal to the negative of the natural log of the magnitude of cosine u plus c. Or this can be written in terms of the natural log of the magnitude of secant of u plus c. To illustrate the use of the different integration rules given earlier, let us work on some examples. Our first example would be to evaluate the integral of 1 plus sine x dx divided by cosine of x. In this given form, it would not fit any one of the trigonometric function rules that we have given earlier. So what we need is to transform the expression. And the way to transform the expression is to divide each of these terms by cosine of x, resulting now to an integral of the form 1 divided by cosine of x plus sine x divided by cosine of x dx. Recall from trigonometry that 1 divided by cosine of x is just equal to secant of x, and the ratio of sine x to cosine of x is just tangent of x. Hence, we will be arriving at this given form. So we have here the integral of secant x dx plus the integral of tangent x dx. To evaluate, we will be making use of these rules. So that for the first term, we will just have the natural log of the magnitude of the sum of secant x and tangent x. And for the second term, it will just be the natural log of the magnitude of secant x plus c. For a second example, let us evaluate the integral of cosine to the fourth x minus sine to the fourth x dx. Again, looking at this form, we cannot fit it to any one of the integration rules given earlier. So for this particular example, again, there is a need to transform the given integrand. Now, how is a transformation done? We will be making use of some principles that we have seen in algebra, considering that what we have here is the difference of the fourth power of cosine x and the fourth power of sine x, recognizing that what we have here is a difference of two squares, where this is the square of cosine squared x, and here is the square of sine squared x. So using now special product technique, where we have a squared minus b squared will just be product of a plus b with a minus b. Then this particular difference we can now express as product of the sum cosine squared x plus sine squared x and cosine squared x minus sine squared x. So we now have the integral of the product of cosine squared x plus sine squared x with cosine squared x minus sine squared x times dx. Again, recalling some trigonometric identities. We have sine squared theta plus cosine squared theta is 1, and cosine 2 theta equal to cosine squared theta minus sine squared theta. Applying that to this particular expression here, then we recognize cosine squared x plus sine squared x to just be 1, and that cosine squared x minus sine squared x, applying this rule, will just be equal to cosine of 2x. Hence, this integral is transformed and simplified to the integral of cosine of 2x dx. To evaluate this integral, we fit it to the form cosine of u du, where our u is 2x and du is 2 dx. So, this integral now would be equal to 1/2 sine of 2x plus c. Okay, remember you need to put in there 2 and you multiply the whole integral with 1/2 to come up with 1/2 sine of 2x plus c. For our third example, let us evaluate the integral of e to the 5x times sine of e to the 5x minus 3 dx. This given integral here we will fit to the form sine u du. So what we do is first to rewrite the integral to this given form. We have the integral of sine of e to the 5x minus 3 times e to the 5x dx. In evaluating the said integral, fitting it to the form sine u du, we pick on the angle or the argument e to the 5x minus 3 as our u function. Its differential is given by 5 times e to the 5x dx, and that the product of e to the 5x dx will just be equal to du divided by 5. So that this integral here can now be expressed in terms of u. Okay, as follows. So the integral will just be equal to 1/5 the integral of sine u du. And in evaluating this integral, we make use of this rule so that the resulting integral will just be equal to negative 1/5 cosine of u plus c. Again, whenever we are making use of u substitution, we should not forget to write back the integral in terms of the original variable, so that this integral now is written in terms of negative 1/5 cosine of e to the 5x minus 3 plus c. Our second example, or our fourth example is to evaluate the integral of x e to the natural log of cotangent x squared dx. Now, this integral can be simplified first. Recall that we have this rule for the logarithms. We have a to the log of x to the base a is equal to x. We can apply this rule in simplifying e to the natural log of cotangent x squared, because this is the same as e to the log of cotangent x squared to the base e, and therefore that will just simplify to cotangent of x squared. So we now have this integral of x e to the ln of cotangent x squared dx to equal the integral of x cotangent of x squared dx. Or you may write it as the integral of cotangent of x squared times x dx, because in this form you can fit it to cotangent u du form. Picking on your u, x squared, the differential du is 2x dx, and x dx will just be equal to du over 2. So the integral is now written as 1/2 the integral of cotangent u du, for which the integral is evaluated on this basis, so that at the end we just have 1/2 ln of sine u plus c, or replacing now u with x squared, we have 1/2 of ln of the magnitude of sine x squared plus c. To recap what was taken up in this lesson, the basic rules for evaluating integrals involving trigonometric functions can be applied for any angle u, a function of x. Integrals involving trigonometric functions, which would not fit initially any one of these basic rules, can first be transformed using applicable trigonometric identities.